Hi everyone, in today's tutorial, we'll build a simple lock-on camera. I'm putting simple in quotes because this version really is very basic. A production lock-on camera would usually be more complex and more customized. First, let's look at the overall result. As you can see, the camera keeps rotating to follow the moving object, while preserving its relative relationship to the character. Let's take a look using ccs.debug.vaewport1 and ccs.debug.vaewport.nodes.all1. You can see to screen space regions, one constrains the eye point, meaning the character, and the other constrains the lookout point, meaning the locked target. The camera moves and rotates to keep these 2 points within their assigned regions. Press Tab to switch to another lock-on target when the target is positioned higher up. The lookout point may not always be strictly constrained within screen space. That's because at high pitch angles, forcing the correction can make the camera tilt upward too abruptly. So we need to relax the constraint in this case. This tutorial won't cover how to make the object move back and forth. In short, you can use Unreal's built-in interpolation component. You can refer to the settings shown here for the exact parameters. In the level blueprint, we call the lock-on camera camera_basic lock-on into places. Later, we'll replace both of those calls with the camera we create. First, create a new camera type asset named CT_test_lock-on-camera. Add a field OFU node. We add this node first because later nodes need the FOV value. 2. Add a screen spacer pivot node. This node constrains a given point within a specified area of screen space. It does this through camera movement and rotation. The white rectangle on screen represents the constraint settings. Here, we also want to constrain the eye point, meaning the character. For the parameters, select actor position, controller controlled pon, 60, and translate. Since we are constraining the eye point through translation. In translation params, set camera distance and interpolator. We don't need to worry about the safe zone related parameters here. Add a lock-on point node. This node calculates the final actual lookout position from the eye point and the original lookout point. In other words, it implements different actual lookout positions at different pitch values. For the follow related parameters, use the same settings as the previous screen spacer pivot. This lets the node know where the eye point is. For the aim-related parameters, select actor position and explicit actor. Since we'll pass in the locked actor from outside later, expose aim actor as a pin. Set pitch range to 70, 60, blend out time to 1, and weights to 0.6, 0.2, 0.2. We won't go through every parameter in detail here. You can check the documentation for that. What you need to know is this: based on the relationship between the eye point and the original look-at point, plus the configured pitch, this node calculates the final point the camera should actually look at. Add another screen spacer pivot to constrain the look-at point in screen space. This time, we directly use the position calculated by the previous node. Set method to rotate, safe zone center to 0.1, 0, and leave the other settings unchanged. The safe zone is the screen space area we want to constrain the point to. Safe zone center of 0, 0 means the exact center of the screen. Width controls how far the area extends left and right from the center, while height controls how far it extends downward and upward. 5. Add a rotation constraints node and constrain pitch to our desired range of 70, 60. 6. Add a collision push node and set the collision channel that completes all the setup. Back in the level blueprint, set camera type ESA to the camera we just created. Now let's check the result. You can see two regions on screen, one constraining the eye point, and one constraining the look-at point. Now let's try another target. Let's slightly adjust the screen space constraint for the follow point. Change it to 0.1, 0, and make both the width and height a bit smaller. You can see that the follow point's screen space constraint region has changed, and it has become tighter. In practice, for the eye point, we usually don't need to constrain it so strictly to a specific screen space region. So here, we can use the same approach as the previous third-person camera. And simply use a basic pivot follow camera. Use the standard chain, receive pivot vector, greater than pivot offset, greater than pivot damping, greater than camera offset. I'll fast forward through this part. Here, we also need to configure a forward offset or tappy, which applies an offset to camera offset, X based on the current pitch. This helps adjust the camera distance based on pitch, making the camera easier to control. We need to configure a curve. I set to keyframes as an example, 1 at 0, 0 and 1 at 60, 160. You can adjust them based on your needs. Back in the game, let's check the result. You can see there is now only one screen space constraint region, and the camera follows the character using the regular follow logic. It also looks pretty good at high pitch angles. But at high pitch angles, the camera follow is a bit slow, which can cause the character to move out of view. In that case, just reduce the damp time value in pivot damping. Now let's check again. This looks much better. When moving at high pitch angles, the character remains visible most of the time. If you need the character to stay visible at all times, you can reduce damp time further. But for this kind of high pitch test, the current result is acceptable. That's it for today's tutorial. In the next episode, we'll cover how to create a spline camera.